Welcome to today's explainer. We're diving right into area, composite figures, and similar Polygon applications. Our learning target for this session is absolutely crystal clear. By the time we wrap up, you'll be able to decompose a composite polygon, choose the perfect area formula using a perpendicular height, and confidently use scale factors to reason about similar polygons. So let's jump in. Here's a quick look at our agenda. We'll cover area versus perimeter, decomposing composite figures, something called the visual area illusion, scale factors and similarity, and we'll finish up with 2 knowledge checks. All right, section 1, area versus perimeter. We're drawing these foundational concepts straight from the OpenStax pre-algebra textbook. OpenStax defines area as the measure of the surface covered by a figure. The absolute most crucial detail here, it is always measured in square units. Just imagine literally placing little 1x1 squares over a surface until the whole thing is perfectly covered. That flat, 2-dimensional region, that's your area. Now, let's compare area with perimeter, because these two get mixed up all the time. Area is that 2D surface inside the shape. Again, square units. Perimeter, on the other hand, is just the 1D distance walking around the outside edge, which only needs linear units. So area is the inside space and perimeter is the outside boundary. Definitely don't want to mix those up. Moving right along to section 2, decomposing composite figures. Let's see how these rules actually play out. Let's tackle our first created practice example. We've got this L-shaped figure here, and overall, it's 8 meters high and 10 meters wide. To find the total area, we just decompose it, or break it down, into 2 simple rectangles. For step 2, we slice it right across horizontally. That gives us a top rectangle that's 4 by 5 meters, and a bottom one that's 10 by 3 meters. Step 3, just do the arithmetic. Top area is 20, bottom area is 30. Add them up, and we get a verified total area of exactly 50 square meters. Okay, here's our second created practice. This time, it's a composite shape with a rectangle sitting right underneath a triangle, and they share a base of 12 inches. Now, pay super close attention to this part. The triangle's perpendicular height is 8 inches, but there is a slanted side labeled 10 inches. Here is the golden rule. A slanted side is practically never your perpendicular height. We absolutely have to use that 8 for our formula. So let's compute. For the rectangle, 12 times 5 is 60. For the triangle, 1/2 times 12 times 8 is 48. Add that 60 and 48 together, and we land at a total of 108 square inches. Section 3, the visual area illusion. We've done the math. Now let's look at a totally mind-bending twist from an illustrative mathematics task. Look closely at this. We start with a standard 8 by 8 square, which we all know has an area of exactly 64 square units. Now, it's cut into 4 specific pieces. But watch what happens when we rearrange those exact same pieces. They suddenly appear to form a 5 by 13 right triangle. But hold on a second. 5 times 13 divided by 2 would be 32.5. And if you look at the rectangle bounding it, the area of the whole shape appears to be 65. Wait, how did the exact same pieces magically gain an extra square unit of area? Are these areas actually different? Well, the secret is in the math, not what your eyes are telling you. If we compare the slopes of the upper edges of the 2 shapes making up that hypotenuse, we uncover the truth. The green quadrilateral has a slope of -2/5, or -0.4. But the yellow triangle, its slope is -3/8, or -0.375. This brilliantly proves our point. The slopes are unequal. That long side isn't a straight line at all. It's actually slightly bent, which hides a super narrow invisible empty gap that adds up to exactly 1 square unit. So, the big takeaway from this illustrative mathematics task is crystal clear. Unequal slopes can hide a narrow gap, meaning a visual impression alone is definitely not proof. In geometry, you simply cannot trust your eyes. You've got to rely entirely on verified mathematical rules. All right, section 4, scale factors and similarity. Let's elevate this explainer and dive into our final concept. So what are similar polygons? Basically, they are figures that have the exact same shape, but not necessarily the same size. You get them through rigid motions like translations, rotations, and reflections, but the real key here is dilations. That means their corresponding sides scale up or down proportionally by a very specific multiplier. We call this specific multiplier K. K represents the length scale factor. And because lengths are a one-dimensional measure, literally everything linear scales by exactly this factor K. That includes your side lengths, your heights, and yep, even the entire perimeter. If a shape's sides double, its perimeter doubles right along with it. But what about the space inside? Well, area is a two-dimensional measure. Because of that, it doesn't just scale by k, it always scales by k squared. Think about it. If you double the length and double the width of a rectangle, the new area isn't just twice as big, it's actually 4 times as big, because 2 squared is 4. Now, before we test your knowledge, I really need to clear up a super common misconception. Just because two shapes have an equal area, that does not mean they are congruent or even similar. You could have a super long, skinny rectangle and a perfect square that both contain exactly 16 square units, but they are obviously entirely different shapes. Section 5. 2 knowledge checks. Let's see you put all of this into practice. Here is check A. We've got a created composite figure made of a 4x4 square attached directly to a 4x6 rectangle. I want you to mentally decompose this figure and compute its total area. Just take a quick second to think it through. All right, let's break down the reasoning. The square's area is simply 4 times 4, which is 16. The rectangle's area is 4 times 6, which gives us 24. Add those two together and you get a verified total area of 40 square units. Nice. Perfect arithmetic step by step. Moving right along to check B. Let's test how lengths and areas scale differently. Imagine you're given a length scale factor of k equals 3 for 2 similar polygons. What is the area scale factor, and exactly how do their perimeters compare? So the answer really reinforces the abstract concepts of proportional scaling we talked about earlier. Since perimeter is a 1D length, it scales strictly by k. That means the new perimeter is exactly 3 times larger. But area is 2D, right? So it scales by k squared, meaning the new area is a full 9 times larger. Section 6. Recap and transfer. Great work today. Let's jump straight to the conclusion and lock this in. Here are your key takeaways. First, area is a two-dimensional measure defined in square units. Second, always verify your perpendicular height mathematically instead of just trusting your visual impression of a slanted side. And third, similar polygons scale their linear lengths by a factor of k, and their areas by a factor of k squared. So I'll leave you with this final thought. How would you verify the area of an unfamiliar composite polygon before trusting a calculator result?